Hello everyone, my name is Gabriel Jung and I am currently a postdoc at IAS in Orsay. Today we talk about primordial non-Gaussianity in the nonlinear regime of the matter and low density fields. This is a long-term project done in collaboration with the many people of the Quijote-PNG team. A key prediction of inflation is the presence of tiny deviations from Gaussianity of the primordial fluctuations, the so-called primordial non-Gaussianity. Depending on the model of inflation considered, this primordial non-Gaussianity comes in different shape and in different amount, characterized by an amplitude parameter called FNL, meaning that any detection would help us to distinguish between these models and to better understand the physics at play in the very early universe. To look for these tiny deviations, one has to go beyond the power spectrum and use higher order statistics like the bispectrum, the 3-point correlation function equivalent in Fourier space, which was, for example, used to obtain the best constraints up to now by looking at the CMB data from Planck. It has constrained primordial non-Gaussianity to be very small, but not yet at a level sufficient to eliminate many models of inflation. But the upcoming large-scale structure surveys like Euclid should be able to improve these constraints, at the conditions that some remaining challenges can be overcome. One of them is the fact that the formation of structure by gravitational collapse is non-linear. This means that the matter distribution at low redshift is very non-Gaussian, and so detecting any small primordial contribution will be very difficult. In addition, doing accurate theoretical predictions is extremely challenging. So we don't even know what is the exact impact of primordial non-Gaussianity on small nonlinear scales. To answer to these questions, we chose to work with simulations. Our goal was to produce enough n-body simulations to study in detail the statistical properties of the matter distribution in the presence of primordial non-Gaussianity. So the basic idea is to generate Gaussian initial conditions at a very early redshift, to which we add a small primordial non-Gaussianity contribution, and then use a numerical code like gadget to follow its evolution up to now. And within the Quijote-PNG collaboration, we produced thousands of such simulations to study the 3 standard shapes of primordial non-Gaussianity, namely the local, equilateral, and orthogonal ones. In addition, all these simulations are fully compatible with the Quijote suite, which has been used in many other works recently. But just to recall, it's a huge suite of n-body simulations that is composed of 15,000 simulations at a fixed cosmology compatible with the Planck results, and many other smaller sets where one cosmological parameter is slightly varied to study its impact on the matter distribution. And I just want to mention that all the simulations cited in these slides are public, as well as the code used to generate them. Once you have all these simulated datasets, the important question is how to extract their relevant information. And when it comes to primordial non-Gaussianity, a standard choice of summary statistics is the bispectrum. To measure it, we use the modal estimator, a method that was originally introduced for the CMB and then later extended to the case of large-scale structure. Its basic idea is to find a basis of functions on which you can write an accurate expansion of the bispectrum with a relatively limited amount of terms. And what remains to do is to estimate the coefficient of this expansion from the data. And so the key element is the choice of modal basis. One could, for example, use step functions in Fourier space, and then the estimator becomes equivalent to a standard binned bispectrum estimator. But we found that it was much more efficient to use simple polynomials. And when I say more efficient, it's really in the sense that with less than 100 mods, we could describe the full information of the bispectrum in the Quijote simulations well into the nonlinear regime, while a similar accuracy with a bin estimator would have required thousands of mods. So it was much faster to compute and also less sensitive to statistical noise. Here we can have a look at some plots of the bispectrum of the Quijote-PNG simulations. And to be exact, it's also divided by the bispectrum of the equivalent simulations without primordial non-Gaussianity. The bispectrum is a function of 3 scales, so here it's shown as a function of 2 of them, k1 and k2, and the third one, k3, is fixed to a given value in each plot. Then the actual value of the bispectrum ratio is given by the color scale, and it highlights the different behaviors of the 3 shapes. On the left, you can see the local template, which is the largest in these left and bottom corners, where 1 mod k is much smaller than the other two. This is the squeeze limit of the bispectrum. In the middle, we see that the equilateral template is the largest when the 3 mods are of the same order. And finally, on the right, we see that the orthogonal template is more complicated because it has both squeezed and an equilateral component. After measuring all these bispectra, the next question is to estimate how much information they contain about primordial non-Gaussianity. And the standard method to do that is to compute the corresponding Fisher matrix, which only requires to know the covariance matrix of the bispectrum, as well as its response to variations in the different relevant parameters, for example, cosmological parameters, and of course, the different primordial non-Gaussianity amplitudes, FNL. Then one can easily compute the best possible error bars on the parameters from the Fisher matrix. And what is important here is that all these quantities can be evaluated from simulations at the condition that you have enough of them. For example, if your sample to estimate the numerical derivatives is too small, it means that it will contain some statistical noise. And this noise can be interpreted as some spurious signal of cosmological origin, making error bars smaller than they should be. And that's why some of my collaborators have worked on an alternative method to estimate Fisher error bars that has the opposite behavior. Instead of giving super-optimal results in the presence of noise, it should give suboptimal ones. This method is based on data compression and the compressed Fisher matrix name. So the principle is just to compute the score function of the bispectrum, which only requires similar ingredients as the Fisher matrix. And what it does is that you end up with a very small set of numbers that contain the same as statistical information as the bispectrum. But because of this compression, in the derivatives of this new compressed statistics, the statistical noise that was present at the level of the bispectrum has been averaged out. And so if you compute the Fisher matrix of the compressed statistics instead of the bispectrum one, you don't have this super-optimality issue. Of course, the noise in the bispectrum derivatives still play a role at this level when you do the compression. But this time its effect is that it makes the compression suboptimal. It means that when doing the compression, you lose a bit of information that was present at the level of the bispectrum. And so you compute the Fisher matrix of a quantity that contains a bit less information compared to the bispectrum. And that's why you end up with suboptimal error bars. And what is interesting is actually that the super-optimality on one side and suboptimality on the other of these two methods are actually of the same order. And so if you compute them in, you could get a good estimate of the actual Fisher error bars with a much lower number of simulations. And finally, I want to mention that with all these ingredients, you can also write this kind of quasi-maximum likelihood estimator, which allows you to find the actual values of the parameter in any new datasets. We have applied all these methods to the Quijote-PNG simulations, and in the remaining minutes of my talks, I would like to present some results we obtained. First, we have a look at the Fisher analysis performed on the matter density field using the bispectrum up to nonlinear scales. and the first plot I'm going to show is really related to the role of including these non-linear scales in the analysis. So here you can see relative 1 sigma Fisher error bars computed for different range of scales using the bispectrum. And as you can see, when you include smaller and smaller scales, these error bars become much smaller. And in particular, between mildly nonlinear scales in green and nonlinear regime in red, you can see an improvement by more than a factor 2 on the 3 FNL parameters. Another interesting result is related to the matter power spectrum. When you include it in the Fisher analysis, you can see that all the error bars are decreasing significantly, and that includes FNL of the 3 shapes, despite the fact that the matter power spectrum on its own is not very sensitive to primordial non-Gaussianity. This effect can be understood when you look at the full power spectrum plus bispectrum covariance matrix, which is very challenging to compute with a perturbative approach. It becomes much simpler with simulations. And basically, it shows that these two quantities are correlated, so having a measurement of the power spectrum helps to distinguish what is the actual primordial part of the bispectrum. All these results were obtained by looking at the matter density field. But of course, in reality, what we observe are only biased traces of it, like galaxies, and that's why we have performed similar analysis on dark matter halo catalogs that were generated from the Quijote and Quijote-PNG simulations to have a more realistic situation. And to summarize, we obtained very similar results, but I would like to use this occasion to discuss a more technical aspect. It is related to the fact that each halo is composed of many dark matter particles of the corresponding simulation, meaning that in each catalog there are much fewer objects than is in its corresponding n-body simulation. And so every quantity that we measured from these halo catalogs is much more noisier than its matter equivalent, including the derivatives of the power spectrum and the bispectrum. And as I already mentioned earlier, having noisy derivatives has an impact on the Fisher constraints that you can derive. And that's something that we can illustrate easily by playing on the level of noise in these derivatives. To do that, we just have to change the number of simulations used to compute the derivatives. And as you can see on the left, when we do standard Fisher computation, when we use less simulations, so when we have more noise, error bars are becoming smaller. That is the superoptimality issue that was mentioned earlier. Then when we use the compressed conservative Fisher method, it's the opposite. Error bars are becoming smaller when we decrease the noise. And finally, when we take the mean of these two methods, results converge much faster to their final values with the number of simulations, and you can see there is more than a 20% difference between the two methods, justifying the need of using all three methods to check the numerical convergence of Fisher error bars evaluated from simulations. All these simulations can also be used to explore alternative strategies to extract relevant information about primordial non-Gaussianity. Recently, we released a paper on arXiv where we tried the halo mass function, so just counting the number of halos as a function of the mass. It has been known for a long time that it's very sensitive to the presence of primordial non-Gaussianity, as you can see in this plot. For example, having a positive FNL of the local or equilateral types increases the chance of having very massive halo quite significantly. And it's the opposite for the orthogonal shape. But the halo mass function is also very sensitive to variations in cosmological parameters, and in the end the different signatures are quite degenerate. So the halo mass function on its own is not a very efficient probe. But it can be combined to what we already had, the power spectrum and the bispectrum, and it gives some very interesting results. For example, for FNL of the equilateral type, by adding the Halo mass function, we got a factor 2 improvement on FNL. And there was also an interesting improvement for the orthogonal shape of around 20%. However, for the local shape, there wasn't any improvement, and that's really related to the fact that all the information is in the scale-dependent bias term on very large scales, and this is already probed at the level of the power spectrum. However, we have shown that the Halo mass function could also be used to break the well-known degeneracy between FNL local and assembly bias, which is a major issue for its estimation from galaxy survey data. To conclude, we have performed the first investigation of the effect of the local, equilateral, and orthogonal shapes of primordial non-Gaussianity in the nonlinear region. One of the main outputs of this work is the Quijote-PNG set of n-body simulations, which is publicly available. We used it to perform Fisher analysis on the matter and halo density fields using standard observables like the power spectrum and bispectrum. We found that there is significant information beyond mildly nonlinear scales, which will be important to use in future observational datasets. We also built and tested an efficient estimator to measure FNL and several cosmological parameters in these simulations. I want to mention that we took extra care to verify the numerical stability of our results by using data compression techniques before computing our Fisher forecasts. Finally, we are looking for more efficient observables than the bispectrum to study primordial non-Gaussianity. I briefly discussed the case of the Halo mass function, but more is coming. Thanks everyone for listening to this video.